So we've talked about the desire to cluster data, which is to find these groups that are sort of hidden in the data, and how, in two-dimensional data like this, it's easy. We can just plot it, right? But in high-dimensional data, because we can't plot all those dimensions at once, it'll be very hard to find them. So we need algorithms to do it for us, and one of those algorithms is k-means. And as I said, k-means works by randomly assigning k of your data points, whatever you set, uh, to the center of k potential clusters, and then subdivides the data into who is closest to those data points, and then figures out where the mean within those clusters is. That's now the center of the cluster, and then it repeats by figuring out who's closest to the new centers, figuring out the mean of those clusters, then figuring out who's closest to those new means, and so on and so on and so on, right? And so let's do it. And thankfully, doing k-means is super duper easy. So we might make a little variable to hold them. We're going to go call it km results or something like that. And into it, we're going to put the output of the k-means function. Our first argument is our data frame. And then we need to say centers equals what, and 3, right? So this is k. This is how many clusters we are looking for. Okay, and that's all we need to do. So we can press enter, and we are done. Now, what has happened here? Okay, so k-means has done this whole process. It has very rapidly picked 3 points because we said, k equals 3. Figured out who's closest, figured out the mean of those clusters, then figured out who's closest to those two means, and so on and so forth, right? Can we view the output? And the answer is, yeah, it's pretty easy. So if we go again and we go plot our data frame, right, which produces this graph that's already up there, but now we say the color. Well, actually, before we do that, let's just have a quick look at this k-means. All right, so if we're in RStudio, if we just click on this, we see what is within this k-means variable we made, and we see there's something called clusters, right? And that is a vector that is as long as how many data points we have. We have 300, and it has a value to say what cluster they're in. So it's saying the first clusters are all in 1, and then it's saying some other things, right? It says where the centers of these clusters are. So it says 1 is at 0.95, which must be 0.95, 0.95. No, it won't be that. It will be saying it's one's at, actually, let's just see this. KM underscore results dollar centers. KM, if I could spell it right. Results. Yeah, all right. So it's saying one center is at 1, 1, which is here. One is at 5, basically 5. So that one there. And one is at 10, 1, which is there. So it's probably done a pretty good job. All right. And so, yeah, so this is what cluster the data points ended up in. This is where the center of the clusters are. We're going to talk about one of these. These are important things, and most of the other things are irrelevant to anything we're ever going to do. All right, so we're going to go back to plot our data frame, and we're going to say our color is equal to the KM results dollar cluster. All right, and so this is going to say for every single data point we plot, what color should we ascribe to it? And by using these numbers, it will say all of the things that are assigned the number 1 as their color will be one color. All of the things that are assigned the number 2 will be a different. Number 3 will be a different color, right? So if we press enter, then we see this, right? So these are the black ones, these are the red ones, these are the green ones. These are the 3 clusters that we found. Now, obviously, we knew this data was there. These clusters were there. It wasn't hard, but this is pretty. At least it works in this case, right? The case where we can see what we know the results are. And if we want to be even fancier, we could go points, which will draw some points over our graph, and we want these to be in the KM results dollar centers, right? And we plot them there, and that didn't work because I need to say, is it this equals 8 and CEX equals 2? Let's see if this works. There we go. Right, that just changed what point, and it drew, before it drew the point too small to see. Right, so we can see where these means are, these three means are. Okay, so K-means, great job, wonderful, great. So we can find our clusters, right? There is one big problem here. This is a non-negligible problem. It is the problem that we're going to be bumping up against all of the time, which is we told it to find three means. And it will find three means. It will cluster the data into three. What if we don't know? What is it going to do, right? If we say, can you find 8 means, is it going to say, I didn't need 8 means, I only needed 3? Unfortunately, it will not do that, right? So if we just copy this, we say k-mean results equals, let's say, centers 4, okay? And we press enter, perfectly happy. So now if we plot our data again, plot data frame where the color is equal to our new k-means results dollar cluster, press enter, you can see it's split one of these clusters in two. So this is the problem with k-means. It will always find as many clusters as you tell it to find. So if you don't know how many clusters are in your data, what are you supposed to do? And the answer is, this is a problem. What can we do about it, right? Now, the answer is complicated, and I could have probably 8 hours going into all of this. We're not going to do it. We're going to do the simplest, quickest, easiest, and we're going to sort of talk about it. And the reason we're going to talk about it in a little bit more detail is because it actually starts to show kind of the problem of this. That is, deciding how many clusters is inherently a difficult problem, right? How would you describe in words what it means to have come to a good solution? You can see it, right? You can see it and go, when we did k equals 3, we got perfect clusters, but what does it mean? And it's something to do with that all of the groups, all of the data points that are together in one cluster are close together, right? There shouldn't be a whole bunch of data points here and then some way far away, right? That sounds bad. So can we sort of measure this? And we can actually. So this thing here called the total within sum of squares, this is that. This is the distance from each mean to all of the other, the distance from each mean to all data points squared and summed up. So the total within each cluster sum of squares. Okay, so we can use this. So let's go and make a new script because this is going to be a little bit long. Right, so we're going to say, we're going to try a whole variety of k values, number of clusters. So we're going to say like k max equals 10. 10, I'm just making that up, right? You probably don't want to go to super high values, but we could go 10. And we're going to make a vector to hold our values. So we're going to go like the sum of squares within equals a empty vector. Okay, and then we can say for k in 1, 2, k max. So we're going to do a for loop where we try each of these k values. And within the for loop, we're going to say, km results, just like we did before, is the result provided to us by k-means, where we put in our data frame, and we say centers equals k. Right, and so we do this once for k equals 1, then we do it for k equals 2, then for k equals 3, right? And then that gets us this, and then for each time we loop around, we want to store this km results dollar total within sum of squares, right, which is the total distance from each data point from its associated mean. And we need to store that, so we're going to, in our vector that we made, we're going to go SS in K contains that. And then when we're done, we're going to plot SS.in. All right, so just think about this again, right? So we're going to say the maximum K value we're going to use, the maximum number of clusters we're going to use is 10. We make an empty vector to hold our sum of squares value. Then we iterate from 1 to K max, and we set K to be that value. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 10. And then we run K-means where we have K-centers and we store the result. And then from that result, we pull out the total within sum of squares and we put it into this vector. You know, we put the first one in position 1 and second one in position 2 and so on. And then we plot it. All right, and let's run this. And here is our graph. Now, to the untrained eye, this is, I'm kind of in the way. Can I move myself? Let's see. Out of the way. All right. Right. So to the untrained eye, this is doesn't look like much, but to the trained eye, this is you'd be very excited if you saw this in real life, because what we're seeing is, well, it's expected that the sum of squares will decrease if we increase K, right? Because you think about, what if there are 300 data points in our sample. What if we had K equals 300? Every single data point would be in one cluster, and the distance from the mean of that cluster to each data point would be exactly 0, right? Because the data points would be sitting on the mean. There'd only be one data point in each cluster, so it would be 0, right? So this curve always ends at, you know, n0. That's where this curve kind of goes down to. But you can see what happens when you get this rapid drop, and then, right? This is called the elbow method. We are looking for the elbow, and here is the elbow. This is the best value of K. This is clear and undeniable. You can see it rapidly drops and then continues across. Okay, now, just in case you don't believe me, let us make a non-clustered data, right? So we'll go back to this one we were making before, feature 1, feature 2. Actually, let's just do two things. Let's make another cluster, right, just to prove. So if I go make another cluster here, I say, let's have mean equals 1 at 10, 10. All right, so we'll put 1 at 10, 10, 10, 10, da 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 da. Let's run that. Right, so now we've got 3 clear clusters, right? Oh, sorry, 4 clear clusters. And now if we run this, where we try our different values of K, we will see the elbow at 4. There you go. Drop, right? So long as your data is clearly clustered, the elbow method works very well. Now, what happens if our data is not clustered? So let's go back to this. We'll just delete these extra variables, right? So we make one big cluster at mean 1, 1. All right, let's run this. All right, here's our data. There's no good clusters in here. I mean, this is the kind of thing where you could start to maybe imagine and squint your eyes and kind of go, oh, maybe there's one big cluster in the middle here, and there's some kind of clusters on the outside, but we know there's not. We made this data, right? There's no cluster in here. This is one just Gaussian cloud in 2 dimensions. Now, if we iterate through this, where we try our different values of K, we get a graph like this, right? There is no elbow. But we know there's no elbow because we made this data. But if you had this data for real and your professor was desperately telling you, oh, I'm sure there's clusters, you might look at n equals 8 here and go, oh, it does kind of drop down at 8 and then kind of go across horizontally. Maybe n equals 8 is the correct answer. Okay. The problem is this looking for this kink in this curve can be quite subjective, and you can find it if you really want to. Now, I won't say nobody is using the elbow method in real life. Unfortunately, people are still using the elbow method, but there are better tools. And They are available to use in R. They're just a bit more complicated to use, and you've got to install extra packages. And I don't want to go down that road. What I just want you to get the idea is that we can run k-means. Running k-means with a certain number of k will always give you k clusters, and if that's all you do, it's very hard to know. But there are some metrics that you can pull out, some measurements you can pull out, and you can plot them over different k's and get some idea of how many clusters there should be. And this elbow method with the within sum of squares is all right if you have very clear clusters, but it can be very ambiguous if you don't have very clear clusters, and you'll see an example of that later.